Okay, I don't know where our classmates are, but I gotta get going. All right. This next section is on regression. So we were talking about how things are correlated, right? So mm, let's see where I put this stuff in there. So that's just like, is there a relationship, right? And how sure are we that that relationship is real? Okay. Now what we're talking about is how can we use that relationship to make the predictions? And if there's a linear relationship, right? What line is the best line to model that relationship? All right. So we will use sample data to find the regression equation, and we will find the best predicted value of a variable using a regression line. Okay. But to do this, we're going to have to remember a little bit of algebra 1. What is the equation for a line? Absolutely. All right. M represents everybody the slope, right? And that tells you how steep the line is. Has everyone heard of this before? And B is the guys, this is like you learned this in 7th grade. It's like the y, it's called the y-intercept, right? Does that sound familiar? Those are the y-intercept, right? So if you have a line that has, so that means that when you plug in x equals 0, right, you multiply m by 0, you end up getting b. Does that sound familiar, everybody? All right, so you have the point 0b, that's kind of like your starting value. And then if this has a slope m, that means every time you go over 1 unit, you go up m, unless m is negative, in which case you're going down, right? How's going on up there? Okay, so definition, the regression line is considered our best line, right? And they call it the least squares line. Why? Well, okay, so the way that it chooses the best line, right? Because if I put a bunch of data, like if I just put a scatter plot and I say, Bobby, you draw what you think is the best line, Mars, like it's not necessarily clear. You and Mars will probably draw a similar line, but it's not guaranteed that it's the same one, right? So here's what it says, right? It says that it's going to find a line, right? So what it does, and this isn't a big part of it, but this is why it gets the name best squares. So here's your data points. And let's say this is a line, right? You can draw down from the data point, you can draw a square. Does everyone understand what I mean? You draw a square, but right, that the height of the square is the y distance between the point and the line. Everyone following? Right? Do we get how we're drawing these squares? We just draw the square up to the line. Okay. Now, the least squared line is the line that right? And those squares would be different for each line, right? So it's the line that minimizes the sum of all of those squares areas added together. Everyone follow? So you draw these squares, right? And you want the squares to be as small as possible. Turns out it's a lot of math, right? That there is one such line. Okay, that's the line that's considered the best line of best fit, right? It uses some statistics and parameters, right? Just there's not much going on here. Just notice that they're using y hat because it's y predicted, right? So for example, if this is your data, not the best, but let's say this is your regression line, right? Here's your actual value of y for that point. This is the predicted value of y. Does everyone see the difference? One of them you actually get from using the equation, right? So, right, just don't worry too much about this. This is just written in slightly different order. B naught is what we would call B, and then this is what we would call M, right? You don't really need to use those notations. So how do we get this? Well, here you have the same requirements before. You shouldn't be using a regression line to make predictions or even creating a regression line unless you have reason to believe that there is actually a linear relationship inside the data, right? So it should be a random sample, and a visual examination should show a approximately linear pattern, right? If the lines follow some sort of curve that's not linear, you're not going to get the right answer. And again, outliers can be problematic. Now, how do I find the slope and y-intercept? Well, I use these equations. But do we want to do this by hand? No, okay? So we're going to use tech, but let me just give you some pieces of information. Right? So here's what is the important caveats here, right? One, before you start using a regression line to make predictions, you should make sure that the following requirements are met. One, that the regression line graphed in the scatter plot shows the line fits the points well, right? If it doesn't, then this whole thing is silly, right? You should also know that your p-value is less than your significance level, and your prediction should not be much beyond the scope of the data, right? What do I mean by that? Let's say this is your data, right? Does this seem like there's a strong linear correlation, everybody? Okay, but I should not be making my prediction up here because perhaps it's linear here, but then like it curves a different direction, right? So if I have data about like people's height and age, like you can imagine this. Let's say aliens only had height data for people from ages 0 to 10 years old. There might be a linear correlation. Would that linear correlation, that same pattern, hold for people in their 30s? Guys, age versus height, is that the pattern that's going to hold for years 0 to 10, is that going to hold in the 30s? No, because you stop growing, guys. Are we understanding this? Because sometimes I'm not seeing anything, right? This is what your height graph might look like in real life, right? So you don't want to use predictions, right, way outside of the data, right? So if you have data that, from 0 to 10, maybe you don't have a data for a 6-year-old, right? You could use an estimation on how tall a 6-year-old would be. You wouldn't want to use it to estimate how tall a 60-year-old is. All right, so let's do this. And then we will show you how to find them here. So here's one that the calculator comes from, and then we will actually find it, all right? So don't do this. This sounds dangerous. Somebody measured the height, widths, and height, what did they measure? Head widths. Guys, can we all pay attention? I feel like half of you don't even look at me, right? So I don't know what the hell's going on. All right, head width of a bear and the bear's weight. How they measure that safely, I have no idea, okay? But they did. For 20 randomly selected bears, okay. When they did that, the bears on average, the mean head width was 9 inches, and the mean weight was 114 pounds, okay? It gives you this R value, and it gives you this P value, okay? So first, let's look at the p-value. So the p-value here is basically, guys, everybody, the p-value here is basically what? And so how would we compare the p-value to the significance value? P to the significance value, guys, how do we compare it? It's what?
The p-value is less than the significance.
Yes. Does everyone see that? So p-value is less than significant. So does this mean that there is evidence of a linear correlation? Yes, right? So since there's evidence of a linear correlation, I'm going to put all these slides up later, but that's all right. And I haven't finished. So since there is, is it valid to use the equation to help us make a prediction? Yeah, right? Okay. So here is the equation that they give us. The predicted weight of a bear is negative . Okay, so this is the equation, right? Everybody, X here represents what fact about the bear? It's not too hard. The bear's head width, and Y is its. Y is not its correlate. Y is its weight, right? So I am trying to figure out the weight of a bear with a head width of 6.5. So what do I do with that 6.5? As this is, I'm literally giving you the answer to the last question of your celebration. So please just listen. What is this correspond to? W, X, Y, Z? X. So this equation relates, right, weight to head width. So plugging in the equation, I end up with roughly 190 pounds. So that's how you use it, right? First, you just have to check that the linear relationship makes sense, right? And then you use the equation to make a prediction, right? If instead I were given a weight of a bear, I would plug that in for Y, and then I'd have to solve X, right? Which you learned how to do like way back in 7th grade. Now, this is what I'm saying, like you can't use the predictions, right, for values that are way outside. So let's say I have a tiny bear and it somehow has a head width of 1 inch. According to this formula, the weight of the bear would be what type of number? If X were equal to 1. This is a hard question. If X were equal to 1, this would be 1. 1 times 61.9 would be 61.9. And I'd add that to negative 220 and 10. 200, negative 212. What kind of number would I get? Negative. Does that make sense? Does a negative number make sense in this context? No, right? So what it's saying is that you can use a linear relationship to make predictions. It doesn't say the data set, but you should only use prediction data value, right? Like X values that are similar to the values that are in your data set, right? You wouldn't want to use a value of X that's much smaller or much larger. Are you following? Right? Because that, and you could see that y-intercept wouldn't make sense. All right. So this is a situation where a relationship makes sense, right? Let's come up with one where it doesn't. And then we'll actually find the relationship here. Okay. So there's the Academy Awards, right? Each year, there is a best, what is it? There's a best supporting actor and a best supporting actress. I mean, people might say, I don't know why there has to be like one of each, right? That seems like why that seems a little, I don't know, old school to me, but that's the way it is, okay? And of course, also old school is that the actresses who win the award are of course younger, right? Whatever, right? But here's the data, right? So the average man, right? The best supporting actor on average is 52 years old. The best supporting actress is 37 years old. And R is 0.07. So that value of R, is that a low or is that a strong value of R or a weak one? Very weak, right? It makes sense if you think about it. Why? Yes.
How do you know, what's is it for example, if it's 0.80, would that be considered a good strong one?
So to get the exact strong, you want to find the p-value that's calculated with it. So we will show you one more example, right? But generally, right, that would be strong. But if it's strong enough to infer that there's a linear relationship, so that means a strong linear relationship, right? But if you see, like looking at the table that we showed you earlier, right? If you have, say, 100 pieces of data, 0.2 is not a linear relationship, right? Well, it's not a strong relationship. But what this would mean is there is some linear correlation, right? It's not by chance, right? But it's still weak, right? So it's saying there's a linear relationship that corresponds to like 20% of the variation we see, right? But right, if you have only a few pieces of data, to know that it didn't happen by chance, you need a stronger value of R, if that makes sense. But again, even though here you don't need a very strong value of R, it's just saying that there's some, we know that there's a weak linear relationship, but it's not by chance. It just happens to be a weak one, right?
Okay.
But we know if it's something close to zero, right? Like that's nothing. And that, in this context, should make sense. Because why would right? There are people probably in different movies winning best actor, best supporting actor, and best supporting actress, right? There should be no, and they're only being matched because it's the same year, right? Like do we get like that the age of the person who wins best actress should not affect the age of the person who wins best actor. So, and that's what this finds here. And we can see that formally because our p-value, right? So what is the relationship between P and the significance level here? So P is greater than the significance level, which means, do we reject the null hypothesis, fail to reject? So that means that there is or is not evidence of a linear relationship. There's not evidence, right? What? This? It's an alpha. I'm not great at. I try. Okay. Well, I don't know. Right. I'm trying now. I'm thinking about it. Okay. Not linear. Okay. Yeah, I know. All right. So if it's not linear, this equation, we can't use it, right? This equation is garbage. What? What do you mean? Yeah, well, so this is saying this is the line of best fit. But like if you graph this it would be like it would look like the crazy scatter plot, right? So the line of best fit doesn't, it's like being the tallest kid in kindergarten, right? You see what I'm saying, right? It's not going to get the job done, right? So if you have to make a prediction, since the two values aren't correlated, right? If I say, guess someone's, I have a friend, Steve. You don't know anything about him. What do you guess his height is? You're going to guess the mean. So, right, it says predict the value of the age of the best supporting actress in a particular year, right? Given that the best supporting actor was a particular age, right? The linear equation, the linear equation is garbage, right? So we don't use that. I wrote garage, my bad. Linear equation is garbage, so we just use the mean. So imagine that, right? So the linear equation shows these two things aren't really correlated, right, in any meaningful way. So if I said, hey, Bobby, guess the age of the woman who won Best Supporting Actress in 1982, based on the fact that I had tacos for dinner, you would just ignore the second part, right? Does everyone see what I'm saying here? So because we know that, that's not correlated, right? Since R here is essentially 0, it's also not correlated. So we don't use the age of the man who won Best Actor that year to help. We don't use the age. We just use the mean because we got nothing. Yeah. Well, we have enough data. It's just like our data shows that they're not correlated. So having X does not help us predict Y. Right? All right, so let's go through like the whole thing, right? Just like a whole example, all right? So probably New York City, because we have the L, but we don't really call it a subway, although, because I guess most of it's elevated, but parts of it are underground, right? Yep. So let's just say this. So this is the cost of a piece of pizza, right? Slice of pizza, 1960, it was apparently 15 cents, pretty cool. All right, and then, inflation, the cost of pizza goes up, the subway fare goes up, right? So here's a good example, Bobby, or anybody, right? Because you remember that temperature thing. Like the cost of pizza does not directly, right? People, the city planners aren't like, what did pizza cost this year? Let's make the subway fare roughly the same thing, right? Yeah. Inflation is caught, but these things are still strongly correlated because they both are related to some other thing, right? The general value of how much stuff you can buy with money in general, right? So let's, again, put this data in our calculator. All right, now let's kind of go through the steps, all right? So first, let's go to, no, we can't see this. I might go over a couple minutes, guys, but trust me, this is basically the exact same thing as your last question on the take-home celebration is, so it'll be worth it. All right, I'm going to memory. I'm going to clear all lists, just so remember the stuff that I entered there before is gone, all right? So second plus sign, option 4. I cleared the list, the diagnostics are still on, right? So that's good. Okay, so now I'm going to enter in the data. You can't really see the data, so I'm going to just hit stat, edit, and I'm going to type it in for you. 0.15, 0.35. You guys remember how to type in data, so I'm just going to switch to the laptop so you can see the data get entered, all right? So you can do that on your own, all right? Everyone remember how to do it? What?
I'm just kidding.
All right, please. I can't. This semester is not the semester to joke about such things, all right? We've had I can't, I don't know what's, I mean, last semester I had a student ask if she could, pay for an access to my lab and do all of the homework after the final celebration. And I was like, no, that's ridiculous. So before we do anything, we want to see if the data like looks linear and stuff. So let's pick a good window here, y'all. What's a good window X, right? So it basically starts at 0, right? I mean, yeah, like 15 cents and 0, pretty similar, right? Like you would eat a lot more pizza if a slice cost 15 cents, right? So 0, and then let's just say 3. And these are roughly the same. So let's do the same for X and Y, right? So let's go to window. So let's do 0 and 3, right? See, you wouldn't be able to see the data before, right? Now, again, right? Regina, if I use 1, there's just going to be 3 giant tick marks, right? So let's make this like 0.3 or something. 30 cents or 0.25. It doesn't matter, right? Let's just do that. All right. So Bobby, on visual examination, is this thing appear to be linear?
Yes.
Visual examination is important, right? If it doesn't even pass that, you can't proceed with anything. Just in that case, you would just estimate the mean, right? Okay. So now we have that. Now we need to actually find out, right? They want us to make a prediction, right? We have, if the cost of pizza is $3, what do we think Subway fare will be, right? So let's do that. So let's find, right? We want to make sure that our p-value is, there's no massive outlier, so there's nothing to worry about there. So let's go to tests. And which test is it? It sounds like we're doing linear regression, so it's lin-reg t-test, okay? So everyone got to this option here, right? Okay, keep this just for linear reg t-test. This screen, just don't change it. Ever, right? And then everything will be good. Okay, so notice our p-value. Hopefully you guys remember this. If you have an E like this, what does that mean? Does anyone know? Yes, exactly, Bobby. So we're looking at a number that's very
No, it's not.
small because the negative, right? That means that means divided by like 10 to the 7th, right? So let me write that down. So our p-value is basically 1.7. Yeah, better. It's good to know that it would give you very different results. Yes, Regina. Yeah, so I did not do the linear regression because that will not give me my p-value.
Yes. So which one was the one that does give you the p-value?
Sure. That was, so I went to stat, and instead of doing calculate, I went to tests. Now, Regina, you could use the linear, you could use R and then count how many years and then use your table on the back to see if it's sufficient, right? That's allowed to, okay? But we're going to use the p-value method here. So to do that, I went all the way down to, it was the second to last option. Lin-reg t-test. And then I left all this stuff, never change it. And then I got this, all right? Okay, so P is basically approximately 0, right? Meaning that P, we want to compare P to everybody. We always compare P to alpha or fish for Mars. right? It's much less than it, right? So that means we can conclude that,
value.
oh, right. No, I should give it to you. I guess I didn't, but how small is P here? Yeah, so it's not really gonna matter, but good question. I tried to pull a fast one on you and Regina didn't fall for it. Okay. So the basic conclusion is, I mean, we would say evidence supports, but since we don't have a ton of time, I'm gonna say it's linear, all right? Okay, now the equation that it gives you is a little bit different. It does A plus BX instead of MX plus, right? It's just things are different, right? Okay, so let's look at our calculator and see what it says, right? So we now know it's linear, but that doesn't really help us make any predictions in of itself. It just means we can use regression, right? That was kind of the first part. It is correlated. So now let's figure out what's the best line. Your calculator now tells us the best line. So let's look at that again. So notice it says it in the linear reg t-test, right? If you ever forget which A and B, notice it gives you the form, right? So it's telling you that this right here is your y-intercept and that's your slope, okay? Does everyone see how to read that? Right, you can also, right, Regina, where you did the linear regression, right, before, it would give you that, but it just wouldn't give you the p-value. All right, so we find out that A is negative 0.0, roughly, right? So our equation then is negative. Does everyone see that I just pulled those values off my calculator? Does everyone understand how I got A and B? So A is my y-intercept. It's just doing it in a slightly different order, right? MX plus B is the same thing as B plus MX, right? No one's confused by that. Okay. So this is the equation that says it's the line of best fit. Now, before just trusting them on it, we should do a visual inspection that it actually works, right? So let me show you how to put in a line. All right, so to graph this, I'm going to go to y1 equals. I'm going to type in my line. So it's negative 0.011. Everyone did y equals. If you have anything else in your y equals, maybe you've used this in a different math class, right? Please take out all the equations, right? X, nope, plus 0.01x. Right, and that's just the equation that it gave us, right? Everyone understood that we got that from the previous window. Now, Mars, does this look pretty good to us? Yeah, definitely, right? So visual confirmation, right? I'm going to make you actually sketch it. I think, did I say to sketch it? Yeah, let's see. So in the take-home celebration, it says sketch it, right? It's basically very similar to this. Right now, this is all just to confirm that I can actually use this equation. Now I should have typed y hat to mean y predicted, right? So now it says if pizza slice is $3, what is the predicted Subway fare? Well, you just plug that into the equation. Pizza slice, that's X. So once you get the equation, it relates pizza to Subway fare. So now that we know that the equation's legit, right? We got the p-value. It seemed linear without the line. We put the line in. It seemed that the line was good. You just do the arithmetic. You get roughly $3 and 2 cents. All right, I know I only did one. Do we all think that we could do that?